Last time I mentioned about the simple queuing system using queuing theory, and which is drilling center with one drill press and one FIFO queue. So there was a labor process and service process, right? And then also departing action, yes, departing action. So this is known as MM1Q, right? Last time I mentioned about the several performance measures of the MM1Q, particularly average number of customer, which is L. So L is a summation between LS and LQ, and LS is a long run average number of customer in service, and LQ is a long run average number of customers waiting in the queue, right? And also there was average time the customer spent in the system, so also known as time in system, so which is W, and W is a combination between WS and WQ, and WS is a long run average amount of time a customer spent in server, and WQ is a long run average amount of time a customer spent in a queue, right? So, and there was a relation between W and L, and we use Little's formula, right, to show the relation between L and W, right? And then also I introduced a state transition rate diagram, including state, arrival rate, and service rate, right? So we use this diagram to calculate the probability of each state with n number of customers in the system, right? So eventually we calculate P0 as well as Pn, and based on this Pn and P0, we calculate the L value, W value, also LQ, WQ, right? In previously. So, and not only the MM1, actually, we also consider the MM1K, right? With the limitation on the capacity, right? Which is K. So, in that case, you can consider the number of state up to K, right? K state. And so you're due to this K condition, so you have a slightly different value of the P0 as well as Pn, right? And of course, you need to consider two different cases when low traffic intensity equals to 1 or not equal to 1, right? So anyway, so you can also calculate the value of L, LQ, W, and WQ, right? For the MM1K. And if if a system has a multiple server, we can use the MM1C queuing model, right, to estimate its performance, right? So in that case, service rate change according to the number of customer in the system, right? So particularly if the number of customer is greater than or equal to C, and then which is capacity, which is number of server, and then service rate becomes C mu, and otherwise it will C minus 1 times mu, right? So that's the service rate. And due to this variability, actually, you will have a different PM value and P0 value as well as Pn. So these values affect the value of LQ, L, WQ, and W, right? Okay, so now utilize this knowledge to solve the problem. And here is we have a practice problem. Let's say we have 10 parts arriving at the facility for processing in every hour, and the labor process follow the Poisson distribution. In other words, exponential, the time interval between parts following the exponential distribution, right? And these arriving parts wait in the queue, so 5 for queue, until one of 3 machine is available to process them. So to process them, in other words, we have 3 servers, right? So you need to use the MMC model, right? And all 3 machines are identical so that they spend the same amount of time to process each part, and machine time of each machine follow the exponential distribution. So now, yes, that's why we have to use MMC model, and here is a parameter, and then so based on that you can actually solve the problem, right? So three machines, right? We have three machines. Also, 10 parts in an hour. So you have a value of the parameters. So please compute the parameters shown here and then estimate the performance of the system, particularly L, LQ, W, WQ. And I already gave you the equations for you, so you can actually calculate the, you can solve this problem. Yeah, I will give the enough time, so maybe I'll give you the about 20 minutes, so you can solve this problem. Yes, in order to solve this problem, you need to find the parameter values first. And actually, lambda value is already given in the problem, right? So 10 parts arriving at the system in every hour. So basically, the arrival rate is 10 per hour, right? And also mu value is what? It's already given, right? So in other words, it's a service rate. So how many entity or how many parts can can get each service can be processed. So 5 parts, right? 5 parts, right? 10 parts per hour will be lambda, and then 5 parts per hour will be the service rate of each machine, right? Which is mu, and a value is mu over lambda. So 5 over 10 will give you what? 0.5, right? So that's a value, and then rho is what? Lambda over C view. So we have 3 servers, right? We have 3 servers, 3 machines. So 3 servers times, and then 5, right? So 15. In other words, 10 over 15, right? Is the low value of rho. And then you need to calculate the P0 and PC as well. However, in order to calculate this complex actually equation, it's better to use the Excel file. Excel, yes. Okay. So let me use an Excel, and then basically let me type lambda was 10, and mu was what? 5, and A was what? 5 or 10, and then rho, I'm sorry, was 10 or 15, right? So let's calculate the P0, and P0 is here, but in order to calculate P0, you have to, let's calculate the P0, and in order to calculate P0, you have to consider these terms. So let me consider the different cases with different k values. So when k equals to 0, and k equal to 1, k equal to 2, right? And then c value, right? Because we have 3 servers, c equal to 3, as you know, right? So we eventually will have 4 terms in this parenthesis, and then k0 value. In order to get this term, actually we need to kth power of a divided by factorial of k. So a, we have value of a, and then times 0, which is 1, right? And the factorial 0 is 1, and factorial 0 is 1. So basically it is 1, right? And then next one is first power of a, so it's a. The factorial 1 is 1, so we have 0.5, and then factorial a square, and then divided by factorial second as 2, and I'm sorry, a should be 0.5, right? And then c, so a is here, and then third power of a divided by factorial 3, right, times 1 over, right, 1 minus rho, right? So if you add all these 4 numbers, you will get the 1.6875 approximately, and as you know, you need to get inverse of this value. So P0 will be 0.5925 or 26, yes, something like that. Okay, and PC, so you have P0, yeah, it's not really difficult to get the value of the PC, and as you know, we have value of a, and third power of a divided by factorial 3, right, times rho is here, right, and n minus c power. So c minus c is what? 0, right? And then times p0. So this value will be the pc. And also, if you wanted, you can calculate the other state probability, but we need only these to calculate the value of L, LQ, right? And then W and WQ. Okay, so yes, let's calculate the L. So it's a rho is here, and then divide this rho by 1 minus rho and square, right? Oops. And then PC is here. So eventually system will have about, wow, so system will have about 0.07 number of customers. Yes, part. So no, this is LQ basically. Yes. Let me just move this. And then L will be this plus lambda over mu, which is A. So server will have this number of customer, right? And then W and WQ. So as you know, you can easily calculate WQ. So LQ divided by lambda will give you WQ. Okay, so this will be the WQ, and then WQ plus 1 over mu is 5 will give you this value. So eventually you will have these numbers, right? Oh, sorry. Yes, these numbers as a solution of this problem.